Black holes represent one of the most extraordinary frontiers in modern astrophysics, regions where the known laws of physics seemingly collapse into uncertainty. Predicted by Albert Einstein in 1916 as a consequence of his general theory of relativity, black holes remained purely theoretical for decades. It wasn't until the mid-20th century that technological advances enabled astronomers to gather compelling indirect evidence of their existence. A major turning point came in the 1960s, when scientists analyzing the star cluster Cygnus discovered a peculiar object, a glowing blue star emitting powerful X-ray radiation while orbiting an unseen companion. Conventional explanations failed to account for this strange behavior. Eventually, researchers concluded that the star was orbiting a massive, invisible object, what we now know as Cygnus X1, one of the first confirmed black hole candidates. Located roughly 6,000 light-years from Earth, Cygnus X1 possesses a gravitational pull so intense that not even light can escape it. This very property gave rise to the term, black hole. Following this discovery, astronomers began detecting more such phenomena across the universe. Current estimates suggest that our own Milky Way galaxy may contain over 100 million black holes. These range from stellar mass black holes, formed from the collapse of massive stars, to supermassive black holes that anchor entire galaxies and influence their structure on cosmic scales. The gravitational influence of black holes extends far beyond their immediate surroundings. At the core of every black hole lies the event horizon, an invisible boundary beyond which nothing, neither matter nor light, can return. Any object that crosses this threshold is subject to a process known as spaghettification, where the difference in gravitational pull from one end to the other stretches it into a long, thin strand. Ultimately, everything pulled in is crushed into the singularity, a point of infinite density where our current understanding of physics fails. Despite decades of research, black holes remain wrapped in layers of mystery. They serve as natural laboratories for testing the extremes of space, time, and gravity. In 2019, humanity took a leap forward when the Event Horizon Telescope collaboration unveiled the first direct image of a black hole, located in the heart of the M87 galaxy, over 50 million light-years away. More than just a historic photograph, this blurry ring of light offered unprecedented insights into black hole dynamics. That iconic image revealed three key regions: the event horizon, the photon sphere, where light orbits the black hole in twisted paths, and the singularity, where known physics breaks down completely. These findings underscore that black holes aren't simply voids, but complex structures governed by extreme physics. What's even more fascinating is that black holes are not all identical. They share a basic structure but vary in size, rotation, and interaction with their surroundings. This diversity complicates efforts to develop a universal theory. Because no probe can survive past the event horizon, scientists study black holes indirectly by observing gravitational waves, X-ray emissions, and the orbital dance of nearby stars. Theories about black hole formation are equally varied. While most are thought to result from the collapse of massive stars, others may emerge from galaxy mergers or the collision of smaller black holes. NASA's investigations into the M87 galaxy's center provide some of the most convincing evidence of the role supermassive black holes play in shaping the evolution of galaxies on unimaginable scales. In 1963, New Zealand physicist Roy Kerr introduced a pivotal concept: rotating black holes, also known as Kerr black holes. Unlike earlier models, Kerr's theory accounted for angular momentum, or spin. A notable feature of this model is the ergosphere, a region just outside the event horizon where space itself is dragged around the spinning black hole. Within the ergosphere, it's theoretically possible to escape, unlike the event horizon. This opened up new avenues in the study of energy extraction and relativity. Today, black holes are no longer relegated to science fiction. They are central to the most cutting-edge research in physics and cosmology. They test the limits of what we know about time, gravity, and even reality itself. Though we may never journey to one, black holes help answer humanity's deepest questions. Where did we come from? What is the universe made of? What lies beyond? At the heart of these cosmic enigmas lies a tantalizing idea. Black holes may be portals to other places, or even other universes. One such concept is the Einstein-Rosen Bridge, better known as a wormhole, a hypothetical tunnel through spacetime that could connect distant parts of the cosmos, or perhaps different realities altogether. This concept, rooted in Einstein's general relativity, treats spacetime as a four-dimensional fabric warped by mass and energy. A wormhole could represent a shortcut through this fabric. While theoretically elegant, the idea is fraught with challenges. Extreme gravitational forces and quantum instabilities could render such tunnels too unstable for passage. Even if they could be stabilized, perhaps using hypothetical exotic matter, relativity still restricts travel speeds, making faster-than-light journeys highly improbable. Despite these obstacles, wormholes continue to capture the scientific imagination, representing a bold vision of cosmic exploration and hidden dimensions. This ties into the broader effort to create a unified theory, a single framework that reconciles general relativity, which governs the large scale of space and gravity, with quantum mechanics, which describes the very small world of particles and forces. One of the most promising candidates for this unification is superstring theory, which posits that all matter and energy in the universe arises from tiny, vibrating strains. These one-dimensional strands resonate at different frequencies to create the diverse particles and forces observed in nature. In this view, the cosmos is a grand symphony, each particle a note in an intricate composition of vibrating energy. Superstring theory has shed new light on black holes, wormholes, and other cosmic phenomena. It also introduces the idea of extra dimensions, hidden realms beyond our familiar three dimensions of space and one of time. These dimensions may be curled up so tightly that they evade direct detection. To visualize this, imagine a creature confined to a two-dimensional surface, unaware of a third dimension above. In a similar way, we may be blind to higher dimensions that subtly shape the universe around us. These extra dimensions might help explain unsolved mysteries such as the nature of gravity, the mass of particles, and even the origins of the universe. Superstring theory has also deepened the connection between theoretical physics and pure mathematics, turning the quest for a theory of everything into a philosophical and scientific odyssey. Yet, despite its elegance, superstring theory remains unproven. The extra dimensions it predicts exist at scales far smaller than we can currently measure. Much of its progress remains theoretical, but its influence continues to inspire new generations of physicists. Recent studies of quantum black holes, where quantum mechanics and relativity intersect, have renewed hope that string theory may provide the key to understanding the true nature of black holes. Physicist Edward Witten once described superstring theory as 21st-century physics that fell into the 20th century, underscoring its complexity and visionary nature. Today, simplified models offer promising glimpses into how string theory might explain quantum aspects of black holes, but scaling these models up to the full 10-dimensional framework is still an immense challenge. The search for a unified theory drives scientists to explore the deepest layers of reality. Solving this puzzle could reveal profound truths about the cosmos. Black holes may not only conceal these truths but also serve as gateways to a new understanding of existence. Their interactions with neutron stars, gamma-ray bursts, and gravitational waves unveil a universe in constant, often violent, motion. As we push the boundaries of knowledge, black holes remind us how much remains unknown. They defy logic, challenge assumptions, and invite us into a realm where science, imagination, and mystery converge. Whether through superstring theory, quantum gravity, or an entirely new discovery waiting just beyond the horizon, the journey to understand black holes is ultimately a journey to understand ourselves and our place in the vast, mysterious universe.